Good morning, still, just. As Lee said, I'm at Nebula. We're not really a security industry company, but I've only been working for them for a week and a half now. So my name's Matthew Garrett. I started off life as a fruit fly biologist. This has actually proven to be very useful in a large number of ways, since fruit flies are complex devices. We have what's effectively an understanding of the sequence that makes a fruit fly. But the problem there is that we have what is effectively the contents of a bytecode language without understanding the interpreter. And then even the bits of the interpreter we do understand, you get output that then has all sorts of weird side effects and rewrites bits of itself. There's no specification. It's awful design. There's just been bits of it that have been re-implemented at length. And the upside of that is that specifications like ACPI and UEFI are significantly easier to deal with than fruit flies. And I'm probably one of a fairly small number of people who have had to deal with worse things before getting to this point of my life. So UEFI was a wonderful breath of fresh air to me. A 2,000 or so page specification describing only the most user-visible bits of UEFI, and then a several volume specification describing the underlying platform initialization stuff. So what is UEFI? In terms of justifying UEFI, it probably helps to have an understanding of what it is and why it exists. It's a replacement for BIOS, BIOS being the code that's responsible for initializing your hardware when you first turn it on and getting it into a consistent state where you can then run an operating system. BIOS originally, well, it actually derives back to CP/M machines. The PC BIOS was based on similar concepts, and that dates back to the original IBM PC back in 1981. BIOS interacting code that shipped on the original PC would still run on modern PCs. It's a little bit concerning in some ways and great in others. The other side of it, it was mostly written in x86 assembly. There were several completely different implementations. There was no specification. The effect was that you had to code to match existing expectations as opposed to code with specification. UEFI replaces the majority of that. UEFI is a cross-vendor specification that's derived from EFI, which was an Intel-only specification for Itanium i64 platform hardware. UEFI is written entirely in C. There's a reference implementation of all the upper layer code that is freely available and usable under a BSD type license, so it can be integrated into commercial products without any licensing considerations. There's a certain amount of vendor value add. Different firmware vendors then extend UEFI or implement certain features in their own way. Platform vendors may then take that even further. If you've bought a modern PC in the past 6 months to a year, it's almost certainly running UEFI, even if you're boosting a BIOS operating system. If you go into the firmware on several platforms, you'll see whizzy graphics and animations and pointy, clicky interfaces. The future is pretty much like Linux desktops from around 2000. But this is apparently a security conference, I'm told. So really, rather than talk too much about the details of the UEFI implementation, I'm going to start talking about security stuff. And what we started seeing, well, okay, we can go back in time and we can say that for an extended period, Windows did not have a particularly strong reputation, regardless of the reality, for security. And that's improved greatly in recent years. The Windows platform's now fairly solid, fairly secure. But one consequence of this is that attackers started implementing malware that was able to run before the operating system could run any security itself. So if you insert a piece of malware here between the firmware and the bootloader, the firmware will execute that, because as far as the firmware is concerned, the malware is the bootloader. once the malware's running, it's able to modify the bootloader, and in turn the bootloader can modify the kernel. And suddenly, even though you thought that you were running a Windows bootloader or a Linux bootloader, and you thought you were running a Windows kernel or a Linux kernel, you're now running a modified kernel, regardless of what's actually on the file system. And there have been... this is pretty much how viruses started. We used to have boot sector viruses that would copy themselves into either floppy disk boot sectors or hard drive boot sectors, and then they'd execute every time you turned on your computer. And those mostly went away when it became easier to just write viruses that attacked the operating system directly. And now, as operating systems become more secure, we're seeing a resurgence in boot sector malware. In some cases, when I've put it in between the firmware and the bootloader here, that's not even necessarily the case. We've seen a couple, I think at least one from China, that was able to flash itself into the firmware on certain motherboards and would then infect your hard drive boot sector, and then the malware in the boot sector would load additional malware and would completely hide itself from the operating system. If the operating system attempted to read that sector off disk, it would be handed back fake results that made everything look okay. If you took the hard drive out and put a new hard drive in order to ensure that you were getting back to a clean slate, the BIOS would reinfect the new hard drive. So this is more difficult to protect against. You can't do this at the operating system level, because if you've run untrusted code before you're running the operating system itself is no longer trusted code, and you can't rely on untrusted code to tell you whether your system's in a trusted state or not. And BIOS has no real way of dealing with this. Some implementations would refuse to execute code unless the MBR looked like a standard MBR. Downside of this is that it wouldn't run any operating system other than the specific version of Windows that happened to have that MBR layout. So this attack vector was left pretty much ignored. Now, how does UEFI change this? BIOS just executed the code that it found in the first 512 bytes on your hard drive, and then that code was responsible for finding the rest of your bootloader and executing that. UEFI is more advanced. UEFI has a partition on your hard drive, the EFI system partition. It's a FAT file system, and on there you have bootloaders, which are just executables. They're, in fact, PECOF objects. They, in fact, say this binary will not run under DOS if you attempt to run them under DOS, assuming you can find DOS on a 64-bit machine. And injecting code into UEFI is fairly straightforward. UEFI is BIOS, in order to use firmware functionality, you called software interrupts, and then that trapped into the BIOS. Code would be executed, and then control would be handed back. UEFI is much more advanced than that. UEFI has function pointers. Any UEFI application gets handed a pointer to a table, and that table contains pointers to other tables, and then those tables have function pointers in, and when you execute them, you get handed back other tables containing function pointers. And then you call those function pointers, and things happen, like reading files off disk, or rebooting the system, or anything. All of these functions are just handled in a straightforward, reasonably consistent way. Great thing about function pointers is that it's really easy to just have them point to something else instead. There's a demonstration at BlueHat this year of hooking a UEFI function pointer such that when the OS X encrypted disk bootloader started, whenever you hit a key, it would stash the key you just hit into NVRAM, and then once the operating system had booted, that could be read out by an unprivileged user. A more advanced technique would have been to use UEFI's network functionality and send all the keystrokes you make in the firmware environment over the network for collection. So how does UEFI change things? It doesn't at the most fundamental level. UEFI is as vulnerable to any kind of pre-boot malware attack as BIOS is. In fact, in some ways, even more so. Operating systems typically don't make use of any BIOS functionality once the operating system started. They do make use of UEFI functions. You could take one of the UEFI runtime pointers, point it at your malware code, and then that code would be executed by the running booted operating system. I do have a point. Part of the UEFI 2.3.1 specification was a usable implementation of what's described as secure boot. Previous versions of UEFI included some of the concepts that ended up turning into this, but not in a particularly usable way. It brings Authenticode to the firmware. Authenticode is the signing technology used by Microsoft in Windows. Drivers for Windows are signed with Authenticode for WinQual purposes. Binaries can be signed for the untrusted binary. This binary was provided by this company, all that kind of thing. So you now can just apply this to the UEFI executables themselves. Like I said, they're just PE-COF binaries. They've got the same file format as a Windows executable. So straightforward to use exactly the same specification to incorporate cryptographic signatures into those binaries. There is a whitelist of trusted signing keys in the firmware database. And so in order to execute, assuming a policy that states that binaries must be signed, the binary must be signed either by a key that is in that whitelist or a key that chains back to a certificate in that whitelist. The alternative is that you can enroll hashes of specific binaries. If you want to run a binary that's not signed, you can take the SHA-1 or SHA-256 of the binary, and you can enroll that. There's also a blacklist. The blacklist can contain either certificates or hashes. So if you have a binary that is signed as trustworthy, and you later find that there's a security flaw in it, if the binary can be tricked into executing arbitrary code, then the hash of that specific binary can be blacklisted. Or if it turns out that a trusted signing key was compromised, that key can be blacklisted. And anything that's either matching that hash or signed with that key will refuse to run. There's then a couple of additional key lists above the signing key list. There's the KEK, key exchange key, and the PK or platform key. You can update the whitelist and the blacklist at runtime as long as the update is signed with a key that's in the KEK database, and new entries can be added to the KEK database if they're signed with the key in the if they're signed with the platform key. So the expectation here is that in the event of any kind of security compromise, Windows Update or another platform's equivalent will just push out an update that extends the blacklist. It's not straightforward for implementation reasons to remove entries from the whitelist. Instead, you just shove them into the blacklist. There's about 32 kilobytes of space to play with, so you can guess a pretty significant number of binary hashes blacklisted. At the moment, there's no significant concern about running out of space. If there is, then with luck, that'll be at the point where systems have more flash available. So this means that you can now state that your bootloader is trusted. The firmware will only execute the bootloader if the bootloader is signed by someone you trust. And in terms of who that person is, the common case is that your hardware vendor has populated the database with their own key so that they can boot diagnostic utilities on the system, and the Microsoft keys so that you can boot Windows. Most devices are sold to run Windows. So since you're running Microsoft's operating system, the assumption is that you probably trust Microsoft. And since you're running the platform vendor's hardware, you probably trust the platform vendor. Either of these parties could be sending all your keystrokes to the NSA if they wanted to. The existence of this signing key doesn't change that. But in order for this to be useful, the firmware has to be trustworthy. If the firmware itself isn't trustworthy, then the fact that you've asserted that the firmware will only execute trusted binaries isn't helpful. Fine, you'll launch a trusted binary, and then if an attacker can get your firmware to execute arbitrary code, the firmware could say that it launched a trusted binary, but actually run anything it wanted to. This is an important distinction between secure boot and trusted boot. Trusted boot is, or trusted boot or measured boot. The idea of trusted boot is that every step of the boot chain updates values in the trusted platform module. And when you get to the operating system can then connect to a remote server. The remote server can pass back a piece of data and ask for the TPM to encrypt the platform state and this piece of data, and then hand it back to the remote server. This is called remote attestation, and it lets the remote server determine whether your hardware is in a known good state or not. Obviously, if the platform's compromised, there's no way for the platform to know whether it's in a good state or not, but you can verify to this remote server that you either are or are not compromised. Secure boot doesn't have this. There's no concept of attestation. The only way you know what you booted in a secure boot environment is that only certain objects are signed, and so you must have boosted a signed object. However, if you boost an unsigned object, that unsigned object can just hook into the functions that allow you to determine whether you booted securely or not, and can just always say, you booted securely. So the fact that the firmware tells you that you booted securely is no indication that you booted securely. You have to believe that the firmware is secure. As well as your bootloaders, you obviously have to trust everything else that executes in the firmware. And that means that the drivers have to be signed. If you take a new graphics card and plug it into a secure boot system, the firmware on that graphics card must be signed by a key that the firmware trusts. And the upshot of this is that if you buy a motherboard now, it will almost certainly support secure boot. But if you plug your graphics card from last year into it, you will not be able to use secure boot on that platform, because otherwise the graphics card driver would refuse to initialize, the firmware would not initialize the graphics card firmware, and you get no graphics output. This is usually considered to be a problem by users for some reason. It also requires that you have EFI drivers for the hardware. Previously, if you were running with EFI and you had a graphics card plugged in, the graphics driver was normally emulating an x86 BIOS and was executing the legacy BIOS driver code in the graphics card ROM. And obviously, since legacy BIOS ROMs can't be signed, that's not permissible in a secure boot environment. So, fine. We say that all of this must be trusted. Your UEFI executables are trusted. Your UEFI drivers are trusted. Your firmware has presumably verified itself and will not permit flashing unsigned firmware. So, OK, you're done. Not really. We're now at the point where your firmware is trusted. Your firmware boots a trusted bootloader. Your bootloader boots a trusted operating system. Your operating system loads an unsigned driver. The unsigned driver turns off memory protection, sets up a fake firmware environment, boots a fake bootloader that then launches a compromised version of your operating system. So if you're watching closely, you might see a boot splash come up and then be replaced by another boot splash. And you've effectively just chained from one operating system into a compromised version of the same operating system. If you can get untrusted code into your kernel, you lose. So we can't just look at this security improvement in terms of the firmware. We need to improve security in the entire stack. All drivers must be signed. And this has been true of 64-bit Windows since Vista, I believe. But now, in Secure Boot, you can no longer turn off the requirement for driver signing. If you want to do driver development, you need to turn off Secure Boot. Command streams to things like graphics cards have to be validated, because otherwise I upload a shader to your GPU that then DMAs malware into your kernel. Hibernation can be a problem. If I can gain administrative access to the system and then modify the hibernation file on disk and then force a reboot of the system, then you'll read this untrusted hibernation data off disk, and then suddenly you're compromised again. No direct access to the hardware, because again, I can just cause the hardware to DMA malware anywhere I want it to. Kernel debuggers, no, you're not allowed to do that. So there's a whole range of things that you need to care about. It's a significant amount of work. As far as I know, Windows has implemented all of this. We've been implementing all of this in Linux recently for the same reasons. Now, we go back here. All code in the firmware environment is trusted. So, of course, it's trusted. We have to trust it. That doesn't mean that we should trust it necessarily. It doesn't mean it's good. The reference UEFI implementation contains approximately 2 million lines of code. This is code that was originally written in the mid to late 90s for IA64 support. It's then had a lot of additional functionality added on top. And we're now asserting that it is within the security boundary. This is code that was not written with security in mind. And as I'm sure we're mostly aware, even when you are writing code with security in mind, that doesn't mean that it's secure code. There are several avenues for untrusted input in the firmware. The most obvious is that, as I said, there's now a file system driver in your firmware. If an attacker can directly modify the EFI system partition, then that code is going to be read by the firmware. And really, file system drivers often tend to not be very good. So if you can manipulate the file system in such a way that you can trigger a bug in the file system driver, there's a good chance that you can then use that to execute arbitrary code. And then you're back at the point where you have a persistent malware infection that is before the operating system started, before you're running any anti-malware utilities yourself. There's a USB stack. There's a network stack. There are many ways that you can potentially attack a UEFI platform. And then this is made even more insane because there is no memory protection. UEFI is, at a technological level, pretty similar to DOS, with the exception that it's running in full protected mode rather than real mode. There is ongoing work in this field. There are patches to the Intel reference code that add stack protection, heap protection, that enable non-executable code segments that do address-based randomization. Phoenix have been working on this in conjunction with Microsoft. So people are working on hardening firmware and helping mitigate cases where there are flaws in firmware. So far, this is not widely deployed. So if you have a UEFI machine right now, then chances are that the firmware has effectively no even moderately recent security features implemented in it. It's really not state-of-the-art. OK. Finally, my presentation was why UEFI. And the reason for this is that we have pretty much, up until recently, been looking at two levels of privilege separation. If you're running on a computer, you're either a user and you can't touch the file system directly, or you're an administrator and you can. But this level of administrative access is overloaded. If you're root and you can touch the file system, you can insert something before the bootloader, you can execute arbitrary code in the kernel because you can load an unsigned driver. These things may be mitigated to a certain extent by mandatory access control. We can use technologies like SE Linux to prevent even root from being able to do certain things. So sure, we have a mandatory access control policy that prevents an administrative user from modifying the bootloader or the kernel. So I just boot another operating system that doesn't implement this mandatory access control and change stuff. Secure boot means that we can have new policy choices. It provides a mechanism for separating the administrative user from owning the entire platform. And this additional layer seems like a worthwhile feature. So using UEFI in this respect means that we can enhance platform security. Now, outside the PC market, the idea of only executing trusted bootloaders is not new. We've seen this on cell phones. We've seen this on games consoles. You only execute trusted code. For the most part, this hasn't been used to protect the user. In cell phones, it's often because the cell phone vendor either has regulatory concerns or it's because they have features they don't want you to use, where the phone is conceivably capable of doing something, they want to ensure that you can't do it. And if that level of control can only be done on the phone must obviously not be permitted to run arbitrary user code. Games consoles, obviously, licensing constraints. The vendors who ship the consoles take a cut from every game sold, therefore they only want games that they've authorized to be sold, where they can make sure they get their cut. Some DRM schemes are based on similar things. The other reason for locking stuff down on games consoles is to prevent users from being able to obtain digital media without authorization from the copyright holder, so making it difficult to rip Blu-rays. If you could execute arbitrary code before you started being able to play a Blu-ray, then it would be much easier to just dump the memory contents out to some external devices you're playing it. Now, in contrast to this, the PC market has primarily thrived through openness. You can run anything you want on a PC you buy. And this has led to all kinds of fun things. If we went back to the 90s, if Linus Torvalds had owned a computer that would only boot trusted operating systems, Linux wouldn't exist. And that might make life easier for a large number of people here. But it is something that has... Competition is helpful. Competition means that we have an incentive to make things better. Without competition, that incentive mostly vanishes. And if the opportunity to do something new, if the cost of breaking into an existing market is now that you need to have the entire hardware supply chain work with you, that makes competition almost impossible. It only allows established players to be involved. So to that end, clear user intent should be respected. When we say that we're looking at improving the security of a platform, that shouldn't mean that it's impossible for the platform to run untrusted code. If the user can express a clear and explicit intent that they want to run arbitrary untrusted code, the user should be able to. An attacker should not be able to. An attacker should not be able to easily manipulate the user into running untrusted code, but it should be possible for the user to run untrusted code. And you can kind of see that in some markets. If you buy one of the Nexus phones from Google, the bootloader in its default state is locked and will only run signed code. If you connect it to a machine, if you run the fastboot command, you can unlock the bootloader. The platform will then indicate on the boot splash that it's in an untrusted state and your warranty may no longer apply. So in terms of ensuring that's the case, Microsoft require that any x86 systems shipped permit, firstly, secure boot to be disabled entirely. That's not really ideal, but if the user wants to run untrusted code, one way of doing that is to just disable the signature enforcement. The majority of x86 platform shipping support third-party objects signed by Microsoft. Now, they need to do that in order to run any external hardware which has an EFI driver built into it. If your graphics card is running a has a ROM containing its driver, and that driver is signed by Microsoft. If that key isn't trusted by your hardware, then your graphics card won't work. They're not actually required to carry this key, but as I said, most of them do. The only cases where you're likely to find a scenario where they're not are devices that have no means of connecting external hardware. So perhaps some x86 tablet-type devices would fall into this category. I've seen no evidence of them yet. On x86 platforms, you're also required to support local key management. It must be possible for the user to enroll their own keys. The means of doing this are wildly inconsistent. There may be a firmware option that allows you to install a key off disk. We've seen one vendor who, depending on which product range you buy, requires that key file either to be a straightforward DER encoded certificate or alternatively a UEFI variable update wrapped DER object. So the same file will not work on both these platforms. On other systems, the only means of doing local key management is for you to delete the platform key, which then means that you can use the UEFI variable update functions. If the platform key is deleted, the system moves into what's called setup mode. In setup mode, you can update the the database of trusted keys without having to sign those updates. So you can install your own keys. ARM is Secure Boot is required for Windows RT devices. It actually explicitly requires that it not be possible for the user to modify the key database or disable Secure Boot on Windows RT devices. That's pretty consistent with the majority of the existing ARM ecosystem. Apple's devices will only boot trusted code. A lot of Android devices will only boot trusted code. A lot of Android devices will only boot trusted code quite badly, and it's actually fairly straightforward to get them to run trusted arbitrary code. But yeah, there are people out there on the internet who appear to have nothing better to do with their life than find ways of making ARM devices run arbitrary code. It's occasionally useful, but really we could possibly find more useful things for these people to do with their time, like, I don't know, cure cancer. Very, very smart people, really terrifying. What we've ended up implementing for the Linux market, where we have Microsoft will sign some third-party objects. Doing that involves purchasing access to the sysdev portal, which involves having to go to Symantec, prove your identity, get an encryption key from them, use that to sign an object that you upload to Microsoft, which then verifies your ID, and then you're granted access, and then you sign objects, upload them, Microsoft review them, send them back to you. We've implemented a shim loader that is signed by Microsoft that permits the end user to determine their local trust policy in a consistent way. So it's a loader that is signed by Microsoft and will only boot codes that it trusts. However, it has an interface for securely adding arbitrary user keys into its trusted key database. This can only be modified at the firmware level, and we've already asserted that everything running in the firmware environment is trusted. The advantage of this is that we can define the file format, we can define what the user interface is, we can then document this for user interaction. But it does require that the platform carry the Microsoft third-party signing key, which is not the key that Windows is signed with. There's the Windows signing key, which everything that's sold with Windows will have, and there's the third-party signing key, which is used for signing drivers and other operating systems. So a system could still potentially ship with the Windows signing key, but without the third-party signing key. And in fact, as far as I'm aware, this is the case for the Windows RT devices. I don't believe that those carry the third-party signing key. Haven't had an opportunity to explicitly verify that, but that's my understanding. So the aim here is to attempt to come up with something where we have end-user control over their security policy without compromising the ecosystem. We're still aiming to ensure that the secure boot world is one where the majority of platforms will only boot codes that the user trusts, and it's not straightforward for an attacker to get in there. So brief summary. UEFI does add additional security. There's a lot of discussion on the internet about how this isn't the case. But it does also involve an analysis of the entire software stack. You can't just add security to your firmware and then assert that your operating system is now more secure. The operating system itself needs to be designed with that in mind. And we can maintain security without destroying the things that made PCs attractive, the hobbyist industry that grew up around them, the home coding that's resulted in people being able to do development on the application ecosystems that we see today. All right, so I'm going to quickly show you a couple of things. The first is there we go. Right, so this is the dashboard for the Windows sysdev portal. So here, if I wanted to get a EFI object signed, first of all, I've gone to Symantec and I've proven my identity. In my case, they want a notarized copy of a government-issued ID. In my case, it was my UK passport. And they want your address. They get very upset if your address isn't from the same country as your passport. I'm not really sure why. So after a certain amount of negotiation with their support people, they told me that if I wanted to sign up using a UK passport, then I needed a UK address. They then explicitly told me that I should just make up a UK address. So in terms of ID validation, there may be a little bit of improvement available. Anyway, once I have that key and I can gain access to the signing portal, you take your UEFI object, you put that inside a cab file, you sign the cab file using the signing key. So in order to upload a file, you both need to have access to the account, the sysdev account, and you also need access to the signing key. So there's a reasonable amount of effort involved in getting into this. You then take this cab file, you log in, and you realize in my case that for some reason the widget that takes the file name is implemented in Silverlight, which for some reason Microsoft haven't released a Linux port of. So I can now happily click this button and, well, OK, fair enough. Let's see. Oh, hey, I wonder what happens when I click this. Wow. Yeah, so there is a open source version of Silverlight called Moonlight. It doesn't actually work for that widget. For that widget apparently uses advanced Silverlight functionality that is not available in the open source version. It's a very nicely engineered upload widget. Still, there's one other thing I should probably show. Yeah, when I was talking about the security of the firmware, it's not particularly secure at the moment in our experience. We did find one case where Intel's reference implementation contained code flow that was along the lines of result equals false. OK? Result equals validation function. If result equals false, return. OK, great. So at this point, if we're going any further, result is true. Then if some other validation function, return status. So if you pass the first validation and fail the second validation, it would return success, which would then skip the bit of code that actually verified the signature. An appropriately malformed signature would always validate. We did tell Intel about this, and Intel, to their credit, then fixed this very quickly by just committing a fix to the repository without flagging it in any way. and then apparently didn't tell any of the firmware vendors. In another case, we discovered that if you set a boot variable to a specific malformed value, you can in fact cause the machine to stop booting. You would think that, okay, worst case scenario, you have to boot off a recovery firmware USB stick. UEFI systems are very nice in this respect. You can, in most cases, dump a copy of the firmware onto a USB stick, and they'll run the copy on the USB stick instead of the copy in Flash. Problem is, the copy on the USB stick would then read the same malformed variable and crash in the same way. Now, once your firmware is crashing, you may have a problem in terms of recovery. Still, that's pretty much everything I wanted to cover. So if there are any questions, I think we've got a few minutes. No? OK. I was supposed to end with some sort of call to action thing.
1 second.
It's the Microsoft way. Yeah. The upshot of this is that we have now moved the firmware inside the security boundary of the operating system. If the easiest thing for someone to do is to attack the firmware, they'll attack the firmware. So we need to consider much more code than we've previously been considering when determining whether an operating system is secure or not.
Matthew, actually, yes, one question. What is your call to action about using UEFI?
OK, that. What I just said. In the analysis, we need to make sure that it is... You've got an operating system. You're working out, is this platform secure? In the past, you would just look at the operating system. Now you need to look at the firmware as well. That's a lot of code that the majority of security workers have no experience with. It's something that's going to be attractive for people who, up until now, have been... those people on the internet who were previously breaking bootloaders on phones, they're probably going to be breaking bootloaders on laptops now. There's going to be a lot of interesting exploits. There's going to be a number of cases where people are going to find that they can get your firmware to execute arbitrary code. And unless you're aware of that, you're perhaps going to make assumptions about the platform security that aren't true.